Now let's take a look at the overflow detection here. The overflows occur when you need extra bits to represent the results here. Overflow can occur for addition of two operands with the same sign. Okay, like you add two negative numbers or you add two positive numbers, or subtraction of operands with different signs. Okay, this is only the possibilities for an overflow. If you, for example, add two different signed numbers, an overflow never occurs. But the idea is checking for the last carry out bits of the operation and check them with each other. And if they're different, it means that there is an overflow here. You check the last carry out bits here together, and this is how we identify if there's an overflow. Or let me try to show this to you with an example. Let's also now suppose that we're having an 8-bit data here, which is where we try to add plus 70 plus 70. Okay, and if you have 1 2 3 5 4 6, okay, 2 to the power 8 bits here, so 0 1 0 0 0 1 1 0 and 0 1 0 0 0 1 1 0 here. You will have 4 bits. They are added together here. What happens here is 0 0 1 1 0 0 0 1, and the output carry is 1. Just focus on this one. Are they different? Are these two different? Yes. So it means that there is an overflow here. Just check. So this one will be 140, in fact, in decimal form, but your capacity here is what? Maximum representation capacity with 8 bits is in signed 𝐤𝐥𝐚𝐲𝐛𝐚𝐜 complement, like signed arithmetic form, right? And from minus 128 up to 127. So it means that there's an overflow here and this flag is up. So if you do this for example, for minus 70, for example, what happens? Just check it again. 1 0 1 1 1 0 1 0 1 0 1 1 1 0 1 0 added together here. Again, you will have, okay, oops, this one is wrong. That should be 0 as well. This is your minus 70. This is your minus 70. And you make the necessary operation here. It's 1. Oops, I'm sorry. There is no carry here. So, okay. Come here. It's 0, 1, 0, 0, 1, 1, 1, 1. Am I doing this correctly? No. This one also should be 1, right? Because of this one. I think now it is correct. So it's okay, 1 and 0. This one was 0. This one was 1. So when you focus these two levels of carry outs here, again they are different. It means that there's an overflow. Not surprisingly, when you add these, you will have minus 140, which is more than the capacity, your maximum capacity of minus 128 here. That's the idea. So you need to have a circuitry here for checking this, right? And you just have a overflow bit here for checking with Cn and Cn minus 1 here. You just use an XOR gate for just connecting them together here, right? These bits, and this will check for your overflow. That's the idea. So there are also other arithmetic functions which makes our designs convenient to based on functional blocks. This is called contraction. We remove the redundant circuitry from our final circuit, so there are some input fixes here. The most popular ones are incrementers, decrementers, multiplication by a constant, division by a constant, zero fill, and extension. You can use circuitry for this. And design by contraction is a technique for simplifying the logic in a functional block to implement a different function. So you just apply the numbers here instead of this one. Just take a look at this example and we will understand it better, hopefully. Just take a look at this. Now we're just having an adder here, but instead we will use it as an incrementer. So it means that you will have your A plus B circuit here for 3 bits directly. So 3-bit operation, 3-bit addition is what you're doing here. But instead of having the second number, you will have here directly 1. So it will be an incrementer. If you use full circuitry here, it would look like this in the above part. But how can you contract it, or how can you minimize this or make it more just by applying 1 0 0 here for the second number? That's the trick. And when you make this, what happens here, if you XOR a number with 1, you will have here a 0 not, right? If it is 0, it will have a 1. If it is 1, it will have here 0. And look at this, your carry in is 0, right? So this one will cancel. What you come here will be 0. And what you have here will be, see, a 0 not XORed with 0. It means that it would be directly this value, a 0 not, and this will be your sum out. So what you have here is a 0 not. And what do you transfer here? A is here, since it is ORed with 0 here. What you have here is A is going to our neighbor here. This is how it travels. All right, so we're done with this part, and there is A coming from here. If you XOR a number with 0 here, what you will have, its value, so it's A1, and you have your A here, and look at this, your A0 and A1 here is ended together and entering. Look at this, here it is 0, and this 0 should be here. Look at this 0 should be here, and your A1 is A1 A0 is right here. You will have your A1 A0 here. See, A1 A0 here. This is going to your neighbor. Great. And what about your sum out here? Sum 1, like a signal. This one is what? It is A0 and A1 coming here and XOR together is your S1. Great. So this is what we have here, and look at this, and this one is coming right here, but I won't have a carry out here because it's an incrementer. I just cancel these parts. And what is my sum out? This one is also not important. When you XOR a number with 0, it would be directly A2 here, A2, and this one is XOR together, it would be your output directly. So the idea is, finally, this circuit is reduced to this one, which is pretty convenient to implement. Now, if you want to have more than a larger size incrementer here, for example, for 8-bit incrementer here, you just duplicate the blocks as the middle cell here. If you have a, for example, 8-bit incrementer, what will happen here? You will have 6 of them here, 6 of them here, connected exactly like this, but this is your first cell and this is your last cell, but you can multiply this block as much as you want depending on the size of your incrementer. That's the idea. So incrementing is adding a fixed value to an arithmetic variable. Usually it is 1 and it is called counting up, but you can have other types of incrementers as well. Not surprisingly, you can provide here any value you like, right? Okay, you provide here 1, 1, 1, and it will become what? It will become a increment by 3 incrementer, right? Okay, that's it. So this is called increment. And decrementing is subtracting a fixed value from an arithmetic variable. It is called counting down. Usually it's 1, and you can also have it in any way. The functional block is called decrementer. And multiplication and division by powers of 2 are pretty convenient. When we make multiplication by powers of 2, we shift left. Okay, if we multiply by, for example, 4, it means that we directly shift left our value to and provide some zeros here. It means that we multiplied the number with a fixed value, which is 4, or division is going right, and the remainder is preserved here. And okay, what you have here is you just provide here zeros here, and you shift right the the number by 2 digits. And there is also multiplication by a constant here, and in order to understand how it works, let me try to show what the multiplier here is. Like if you're trying to have a multiplier like this, this is your multiplicand, and this would be your multiplier, right? This is how you do multiplication at all. See, we will have a multiplicator by 5. See, multiplicator by 5, and this is your input number. Okay. So it means that this one will be directly 1, 0, 1. So you will have here what? You will have, okay, let me just write it openly first, then we will reduce it. What you have here will be A0, B0, A0, B1, A0, B2, A0, B3. So I make this multiplication, and I do for this, okay, A1 next, A1, B0, A1, B1, A1, 2, A1, B3, perfect. And finally this one, and it would be what? A2, B0, A2, B1, 2, B2, A2, B3. Finally, we add them all together, right? But we should keep in mind that this one is 0 and these all will be 0, right? So we don't have them. And when we make the multiplication, additions in this manner, let's see what happens. So your results will be it's A0, B0. Look at this. Your A0 is 1 and your your A0 is 1 and your A2 is also 1. So it is the 0. So okay, let me just try to, okay, let's say that these are your outputs: C0, C1, C2, C3, 4, C5, and finally your carry out here. This is your carry out. And what is your C0 here? It is B0. And what is your C1 here? It is your B1. And what is your C2 here? It is B0 plus B2. And what is your C3 here? B3 plus B1. And what is your C4 here? It is B2. And what is your C5 here? It is B3. So you will have B3, B2, B1, and let me just put it like this. It would be much more beautiful. B0. Look at this. This one, and this one, 0, 0, added together in a 4-bit ripple carry adder, and these will be your direct out. This is in fact what we have here. You see? Look at this. What we have here is these are coming directly. See? Here is these are coming directly. And what is your C2 here? It is B0 plus B2. See? These ones. Oops, I write this wrong here. Okay, let me just correct it fastly. I made a mistake. I'm very, very sorry here. This one should be, of course, one should be 0 and 0 here. So it would be, anyway. So it would be B3 plus B1 here, this one, B3 plus B1 here, and the remaining ones are, what is it? It is B2 plus 0 and B3, and this one would be your carry out. This is what the contracted form of this multiplicator. In fact, normally if you want to have this structure as a full circuit, it means that you need to have 2 levels of binary adders, right? Let me just try to show this to you. Look at this. For this one, you need to have a full adder level. This can come directly, it's okay, but for this one you need to have a full adder. And for let me use blue here. For this one you need to have another full adder again, right? In fact, this should be 2 levels here if we didn't use constants. But since we used the constant here, we were able to do the contraction and reduce the circuit into this one. That's it about multiplication by a constant value. And what about the zero fill? Is filling an n-bit operand with zeros to become an n-bit operand with where your n is greater than m. It is usually applied to the most significant bit, but it can also be done on the least significant bit n2. This is your data, and it will be filled to 16 bits, for example. Your 8 bits is filled to 16 bits here. If you fill the zeros on the most significant end, the data will look like this. If you fill the zeros on the least significant bit side, right side, it would look like this. Zero fill is pretty straightforward. In extension, you're just increasing the number of bits at the most significant end to represent mathematically the same value here. So it's for zero fill, you don't care about the the value here, so it may change, but here the value will be the same. Suppose that you have a original data like this. When you extend this, since it is a positive value, when you extend this, you fill all zeros here. But suppose that your data was like this, it means that this is a negative value, so you fill only a series of ones here to make the extension. So this was about the arithmetic functions in this chapter. Thank you for listening.